Okay, we are recording. New attendance here. Aki, A-K-I-H, last name, not here. Blount, last name Blount, B-L-O-U-N-T, not here. Boggs is here, Bonner is here, Clay is here. Clayton, last name Clayton, not here. Dawson's here. Ellis, last name Ellis, not here. Paul is here, Green is here, Harrison's here, Henson's here, last name James is here, Kesterson is here, King is here, Lewis is here, and the Q just came in, right? Right. Morrison, that's what was throwing me off. For some reason, I was expecting to be sitting over here. You can sit wherever you want, but sometimes my brain gets stuck with the last place I saw you. First name Grace is online. Excuse me, Rice is online. Ward is here. Wilcox is here. Wilder is here. Parks, not here. Did I miss anybody? Close the door, we'll get started. So, reminder. Pre-lab for lab 1 is way past due. It was due Friday. If you haven't turned it in yet by Friday, I sent you an email saying, hey, make sure you get it done. So if you haven't had it done yet, meet me on, must mean you need help. So meet me at 9 a.m. or sometime between 9 and 10 today online for office hours so I can help you with it. I know at least one person is already scheduled, so I'll be helping them. So otherwise, I will take questions for that, but let's move forward. Like I said, if you need help, let me know. What else? Get some independent work done. One student did a lot and it was good. And that student, if they're willing to tell you, can tell you it's a learning curve, right? This is why I want you to get stuff turned in early, because you'll learn like all these little rules I have. And I've already given you so much information, I don't want to give you all the little rules I have. So the best way to do it is trial and error. You turn some papers in, I say, hey, that's good, but next time don't do this. Turn something in, maybe I'll be like, oh, I can't accept this. Please reply and fix this thing. You know what I mean? So get some experience. Like I said, the best way to write a paper, in my opinion, if you don't like writing papers, just think of a question and answer it. 2-sentence paper. Just wondering where cats are the most destructive. I looked it up, and they're the most destructive in Australia. That's true. Just made that up. So any questions about anything other than the actual course material before we jump into the course material? Hopefully today we will finish up chapter 1, start chapter 2. And then it starts getting a little bit more entertaining, in my opinion. Even if you don't like chemistry, I still think it's better than some of the stuff we're talking about. So anyway, last week we finished the first half of this chapter. We talked about the themes and the concepts of biology. In a sense, we kind of talked about what biology was, right? Which is the scientific process of life. So we talked about life, right? And here, now we're going to focus on that other part of the definition, the scientific process of life. So we'll talk about the process of science. The learning objectives, here we go. I know it's hard to read, but by the end of the section, you should be able to identify the shared characteristics of the natural sciences. But did we already do this? We did? You guys don't be afraid to ever stop me. What happened is, when I pulled this PowerPoint up, it says, it's got a little icon that says, come here and start where you left off. Which is what I did, but apparently somebody can mess up my PowerPoint. So let's see. Talk about theories, talk about that, talk about fact, talk about that, talk about the different types of reasoning. We talked about this. Scientific method, we talked about that. We'll pretend like I didn't do this on purpose. So see if you remember wherever that from. It's not that I forgot over the weekend. Oh yes, we talked about this. Independent variable versus dependent variable. Yeah, that's it. I do remember now. So we haven't talked about placebos yet, right? Good. I'm gonna go through this quickly. This isn't from your textbook. I'm most likely not gonna test you on it. This is from your old textbook, but it is worth mentioning because, like I said, biology is important even if you're not a biology major. And one of the reasons biology is going to be important for a non-biology major, unfortunately, will be for medical reasons, right? Whether you are sick, or someone you love has a disease, or someone's trying to sell you on taking a medication, or someone's trying to turn you off from taking a vaccination, whatever it may be, you need to have a little bit of medical literacy. And you're not going to get a lot of it in this class, but this, again, we'll get into the basic foundation. So let's talk about placebos. Who knows what a placebo is? Yes, sir. Yeah, it's like you're giving them a treatment. They think it's a treatment, but you're not actually giving them the treatment. First word for attendance will be treatment. So again, if you guys are in person, send me an email afterwards, after class, but before 9 a.m. if you can get extra credit points. If you're online, make sure you send me one email at the end with all these words for your attendance. And Ward, when you do it, remind me that you correctly answered that question. A little bit more extra credit. Yeah, that's what a placebo is. It's a medically ineffective treatment, right? It allows the placebo group to serve as a control group. So we talked about that last week. That's one of the last things we talked about was the control group. So when you're doing experiments, you need a group that doesn't receive the experimental treatment. Hopefully by now all of you have been in the lab, in which case you read about that hypothetical plant situation. That's a bad example. We'll use the other hypothetical plant situation I talked about last week, the urine thing, right? So the whole idea is urine good for plants or not? So in that experiment, you would have a bunch of plants with varying amounts of urine, and then you would have one that just gets water, right? That would be the control group. So again, the medical studies, the placebo group is the control group. Typically, the placebo group doesn't know they're receiving the ineffective substitute, almost always. Mind's a powerful thing. You can get into that. You can write papers about that if you want. But again, I'm going to go through this quickly. This is not your textbook. I'm probably not going to test you on it. A double-blind experiment, that is when the participants, or neither the participants nor the people doing the study know which ones, right? So if I were doing that study, if I were giving the study, and it was a double-blind experiment, I would be giving people like, all right, you get drug A, you get drug B, you get drug C, you get drug D, and I don't know which one is the placebo. That's how a double-blind experiment works. Did I talk about this? Yeah, no, we haven't talked about this. All right, so this is an example from your last textbook. I think it's a great example. If you remember in the beginning of chapter 1, I talked about how people use the scientific process all the time, right? You're using the scientific method, even when you're not thinking about using the scientific method. And your old textbook uses this as an example. Can anybody tell me what that thing is? Yeah, it's a remote, right? So let's say you're leaving here, done with school, you're done with your work, you want to go home and watch something. Click the button to turn on the TV, and the TV doesn't turn on. That's your observation, right? So what are some questions? If you click the thing and nothing comes on, what question might you ask yourself?
The battery dead.
Oh, yeah, I like this. You guys went straight for the hypothesis. But what question would you ask yourself before you say, hey, the battery's dead?
Why isn't it turning on?
Yeah, why isn't it turning on? But I also like that you guys straight for the hypothesis because, again, the scientific method is just a general guideline. Sometimes you do skip steps, right? So you might just you might click it, nothing turns on. You might automatically, instead of, all right, what's the next step in the process? No, you don't do that. You just might all of a sudden come to a conclusion, which is the battery's dead. So yeah, that's a hypothesis. The battery's dead. What's another hypothesis? When you click the red button and your TV doesn't come on, one hypothesis is the battery's dead. What's some other ones?
It's the TV unplugged.
Is TV unplugged? What else? This is the button work, right? The button could be broken. Maybe the age of it, right? There's so many different hypotheses. Here's the example from your old textbook, right? Your exploration stage is you trying to turn the TV on, it doesn't work. So then you have the hypothesis, again, there's a lot of different hypotheses, but the one we're going to talk about is the remote's batteries are dead. So it's kind of cool that you guys went straight for that one. That's the one they use in the example. So, again, there's this relationship between a prediction and a hypothesis. The prediction basically describes how you're going to test your hypothesis. So if your hypothesis is that the remote's batteries are dead, you would predict if I replace the batteries, then the remote will work, right? Or then the TV would turn on, however you want to say it. It's an if-then statement, generally, kind of describes how you're going to test the hypothesis. So you do that. You change the batteries. You replace it. That's your experiment. And the conclusion either supports your hypothesis or it doesn't, right? So if it turns the TV on, your hypothesis was correct, right? The batteries were correct. If you put the batteries in there and it's not working still, then you need to come back here and form a new hypothesis, right? Because your TV's still not working. The only thing I don't like about, well, no, this is a great example of how people use the scientific method in the real world without even thinking of it. But of course, if this was a real scientific method, what would really happen, and I like that they included this, let's say you replaced the batteries and it worked. In the real world, you're done, right? You're going to watch Walking Dead or whatever it is you're going to watch. But in science, just because your experiment supported your hypothesis, it doesn't mean you're done, right? Then you would come back and find out a new way to test your hypothesis. But of course, that's not realistic in real life. When you're trying to turn the TV on, if you turn it on, then you're done. Any questions about that? All right. I'm not going to read this to you. I just gave you a lot of examples between hypotheses and predictions. Sometimes people have issues trying to understand the relationship between the two. So if you do, then download this PowerPoint and you can read this PowerPoint. I'm not going to test you on any of that. It's just that historically, that's usually what people would ask me a lot for from this chapter is more examples of the relationship between hypotheses and predictions. And again, I put a big X that indicating I'm not going to test you on that exam. All right, let's talk about basic science versus applied science. Yeah, I feel like I've already said this. Have I not said this? Okay, good. Deja vu. Oh, that's because I'm going through old videos of my old lectures. And it's throwing me off. Anyway, the difference between basic science and applied science. Basic science is also known as pure science. It is science for the sake of knowledge. And that's basically what I did for my thesis work when I was trying to figure out the genes responsible for trichomes. That's just because no one else had ever figured it out before, so I wanted to figure it out. I just wanted to know what were the genes responsible for the trichomes on watermelon plants. That's it. Applied science, also known as technology, is problem solving. And very often they overlap. Using the same example, my purpose for trying to find the genes for trichome development in watermelon plants was basic science. However, trichomes are very beneficial for plants. They help protect from insects. They help protect it from abrasions. They even get a little bit of UV protection, right? So what I was looking for is actually commercially beneficial. So it could be applied science if I did the same thing, but my goal was to find the trichomes, so I could, breed a better watermelon plant or create some sort of GMO that had a lot of trichomes, right? So it would be the same thing, just different goals in that example. I'm not sure if I'm going to ask any questions about this on the exam. It's pretty basic. So that's what the question mark's for. I'm not sure if I'm going to ask. But yeah, basic science, strictly for knowledge. Applied science, problem solving. Any questions about that? All right. The last portion of the scientific method is reporting your work, right? And this is where we talk about publishing stuff in scientific journals. This is probably actually one of the more important things for you, in my opinion. You're not going to probably read a lot of peer-reviewed journals. And then unless you're in science, you're almost definitely not going to write an article one. But hopefully, as a critically thinking citizen later, you will read some peer-reviewed journals. Hopefully, you won't just take people's word for it. They say, I saw a meme today, and once I've done grading, I'm actually going to go fact check the meme just for fun. I'm not going to share it with anybody and correct people, but it said something like 90% of the food we eat today didn't exist 90 years ago, and neither did 90% of the diseases, which is mostly probably BS, but they're definitely implying that it's the food, which I'm sure has a little bit to do with it, but there's a lot more than things. Anyway, point being, hopefully when you're confronted with people trying to sell you on something, you do a little bit of thinking for yourselves, and don't just believe it just because you happen to like the narrative. And that's what brings us to this. So before an article can be published in a scientific journal, the research has to be evaluated by qualified, impartial, and often anonymous experts that were not involved in the study. So the work that I did, well, they're still working on the work that I did. The trichome thing was a small part of a bigger project. Anyway, once that is done, it'll be submitted, right? Submitted to be published. And before it can be published, that's what happens, right? People we don't know, but that are experts in the field, they're going to look at the studies and see if it's legit or not. And again, the purpose here is to provide quality control. That's what peer review is. It's not perfect. Sometimes things get retracted. Sometimes things make it through the peer review. Sometimes garbage makes it through the peer review system, and garbage does get occasionally published. But it's the best thing we have. It's better than some guy on YouTube saying, I did my research. It's got nice flashy graphics, but really didn't do any research. There's no quality control there. It's so important these days. There's so much misinformation. I call it the misinformation age. You could think of any crazy question, come up with some crazy explanation for it, and find it on the internet, I bet. Anything you can think of. Like, I don't know, the correlation between how much hair a man has on his chest and how violent he is with his kids or something. I don't know. I just came up with that in my brain, but I bet if I were to look on the internet, I could find somebody's written something on it. Like, yeah, hairy men are the worst. Anyway, peer review, very important. Not necessarily for this class or for the exam. The peer review in your life should be very, very important. And we'll talk about that. A lot of times in your independent work, this is why I love independent work. Someone here is going to do this. Actually, most of you probably will. You're probably going to turn in some garbage. And it won't be your fault. But I'll just say, hey, full credit. But just so you know, that article's really old. You should have paid attention. That's an old article. Now you know better. Or that's not even peer reviewed. You know. So I'll correct you so you can learn from it. But unless it's like complete garbage, like in the tabloid, you're not going to lose points for it. But it'll be a learning moment, right? Anyway, any questions on peer review? All right. So the next word, I guess, phrase for attendance, be chest hair. Anyway, let's talk about evaluating scientific claims. Again, this part's not in your textbook. It's so important. This goes along with what I've just been saying. In this misinformation age, especially during an election, there's something called pseudoscience. It's the field of study falsely presented as having scientific basis. It's everywhere. It's not as bad as it used to be. COVID brought out a lot of pseudoscience.
It's just like the false advertising that we get on the TV.
Yeah, a little bit, yeah. But more so, it's definitely false advertising, but this is specifically like where they're trying to make it seem legit. We'll talk about that. Several indicators. I'm almost definitely not going to test you on this, but this is very important to know. Anecdotal evidence. So that's evidence that's based on a single or a few examples, but it doesn't support generalized conclusions. Again, vaccines are a great example of that. Vaccines have been shown, depending on which vaccine they did, well, they're all been safe. Different varying degrees of safe. There's always a risk of something going wrong. But the numbers show, statistics show, that depending on the vaccine you're talking about, it's almost much safer to get the vaccine than to risk not getting it and getting the disease. There's a lot of different vaccines, so it's blanket safety. However, right, so that's the statistics that will tell you, all right, it's safe to take this. But let's say you know, like, I don't know, cousin Becky took a vaccine, you know, she's a healthy athlete or whatever. 1 week later, she dies of, I don't know, some kind of heart failure or something. And then in your brain, like, vaccines are really dangerous, right? It doesn't matter what the numbers say. You saw somebody die and you loved them, right? That's anecdotal evidence. And sadly, anecdotal evidence, as useless as it is scientifically, it's very powerful. A lot of pseudoscience, they use this, right? Anecdotal evidence is so strong. Like, how many of you, I don't know, are afraid to swim in the ocean because of sharks or drowning or anything? Well, drowning's not a good example. Sharks, right? Sharks. Yeah. Okay. Well, if it is sharks, you know, statistically, we know it's not that dangerous. But there's fear, right? You've seen the show, not the shows, seen it on the news where people get attacked, which is very rare. But when it happens, that's anecdotal evidence. You see it. You hear the story, and you imagine yourself getting bit by a shark and how terrifying that must be. For me, a good example is flying. When I was in the Marines, I fixed jets. So now, every time something goes wrong in a plane, I'm scared, right? So I don't like flying anymore. But this is where it goes about anecdotal evidence. Sort of. This is kind of pushing it a little bit, but we know statistically that the most dangerous time to be on a plane is when it lands, so when it's taking off. That's the most dangerous time. When you're flying, generally speaking, you're okay. But that doesn't matter. In my brain, when we're landing, I'm calm. I'm like, thank God this is over. And when I'm up there, I'm like, my brain's thinking about all the things that could go wrong, crashing, and have to be alive for those few seconds, knowing I'm about to die, right? That scares me to death. So that's not necessarily anecdotal evidence, but the point is there that it's your brain can ignore statistics when it gets too much emotion involved, right? And that's what anecdotal evidence is for, is getting emotion involved. Any questions about anecdotal evidence? All right. The next thing you need to look for is a source of information. Really quickly, I'll give you this example. Back when Burger King came out with the Impossible Whopper, that's the meatless Whopper. Saw a paper saying it was, I don't remember the negative side effects, but some paper saying the negative side effects of the Impossible Whopper. I followed, it was just like a regular old article. And then that regular old article linked another article. So I clicked that, read that article, and that still wasn't the source of the information. So it had a reference, so I clicked that. I went, dug, got to the original source of the information, which is important to do if you're trying to find pseudoscience. And the person who had written that paper, basically, or that article, basically about how bad fake meat is, was the president of some kind of veterinary organization in Texas where they work on cattle, like cattle vets. He was the president of that organization, writing a paper about how bad fake meat is. Go figure, right? So look for your source of information. Is there a bias there? A lot of times that turned out to be pseudoscience. And that was my first red flag, was where did the information come from? And then once I found out it was from that guy, then I really started digging into the paper, like, oh, yeah, that's BS. Anyway, again, source of information. Was that information peer reviewed? The one I read was not. Was this from a company trying to sell you something? Which I love that too. People are like, oh, you're eating all this garbage from the grocery store, and it's bad for you, and it's just big pharma and everybody trying to make money off of you. But you can buy my supplements for $10. Like they'll try to tell you, like, people trying to make money off of you, and then turn around and try to sell you something. Anyway, if you download this PowerPoint, this is handy to have. It's a great little table that shows you the difference, the features of science versus the features of pseudoscience. And again, as far as the exam is concerned, and this semester is concerned, it's not a very important concept. But as far as your real life is concerned, this is very important. There's a lot of misinformation out there. Here's another thing, again, if you were to download the PowerPoint, this is also very helpful. If you're really good, if you really have the time, when you're writing your independent work, this is a checklist that you should do. I'm not asking you to. It'd be really cool if you did, but make sure, is it current? Is it primary? Meaning, like I said, that article I read, I clicked their reference, which brought me to another reference, and I kept going until I got to the primary source. Anyway, I'm not going to read all that. You can read it yourself. We'll save some time, because that is the end of chapter 1. We can now jump into chapter 2. Any questions about chapter 1? And again, in my opinion, this is probably some of the more important stuff that you're gonna look at, definitely today. But let's move forward. Now go to the next one. Sorry for the wait. While I'm pulling this PowerPoint up, does anybody have any questions about chapter 1, the lab, or independent work, or anything in general?
So, how
Off the top of my head, I would say the majority of the people have not been graded yet.
that would be under 5.
And the grade book? In the grade book, that's a good question. So your grade for lab 1, for example, will be put in once I grade lab 1, like once you turn it in this Friday. At that point, I'll combine all your pre-lab grade, your lab grade, and I'll go into WBSU Online, and that's the number that I'll get. Great question. I might as well do this way so I can show you what I'm doing, so you can do it as well. There we go. So if you go to the course, and there's a couple ways. I like the little click here. It's a shortcut. So there we go. Chapter 2, chemistry. Nope. That's the chapter in the textbook. What I'm looking for is the PowerPoint. There we go. PowerPoint chapter 2. It's on Google, so you can view it. Or do what I'm going to do. Just download it. And download will be the next word for attendance. Come on. This is killing me. If I go like this, so I can actually see what I'm doing. There we go. While that's downloading, So I posted a few things on Facebook to the group, if you guys in the group. Might as well verbally announce it, especially since we have student athletes in here. Generally speaking, if you go to unless you have to, unless you're the athlete, if you go to support an athlete, go to an event, prove that you were there with some pictures, I'll give you some extra credit. Or there's other things you can do to get even more extra credit. We'll talk about that later. Just wanted to throw that out there while I'm waiting on this to download. So how many of you took biology because you didn't want to take chemistry? Okay. So there's good news and there's bad news. Obviously, the bad news is we're about to do chemistry. Good news is it's a lot easier. This is the really easy version of chemistry. This is not the hard version. There's almost no math involved, almost no math involved. It's very, very simple. How many of you had chemistry before? Okay. So you've balanced equations, maybe? Done some stoichiometry? Anyway, none of that in this class. So this will be pretty easy. Let's start. Again, this picture is from your old textbook. I love that your old textbook kind of starts with a little guessing game and brings up some current stuff about chemistry and why it might actually matter to you. How many of you are chemists? Okay, didn't think so, right? So why would this matter, right? Let's talk about it. This is my favorite. I'll start with this one. Easy picture to guess what it is, right? What's that a picture of? Fries. Can you see what's being poured onto the fries, or is it too blurry? Salt, right? We assume. I mean, technically, it could be sugar, cocaine, we don't know. But yeah, probably salt. The reason I like this, what their book, the old textbook is getting at here, is that salt is something you deal with all the time, right? You need it. You need salt. You have to have salt in your diet. Who knows what happens if you have too much salt, though? Generally speaking. High blood pressure, right? It's not good for you to have too much salt, which is something I'm going to harp on a lot in this chapter and then throughout the semester. Everything's poisonous. Even things you need is bad for you if you have too much. So when someone's trying to sell you on some garbage, especially chemical stuff, right? The people love to be trying to sell you on some chemical garbage and scare you when you don't need to be scared. When they say it's bad for you, oh, look, it does this to you. Yeah, everything's bad for you, too much. Too much oxygen's not good for you. Too much water will also kill you, right? Everything's bad for you. So it's all about the poison makes the dose. Another thing they'll try to scare you with, and they won't do it with salt, but they'll try to say, ooh, this ingredient is in here, and that's a scary ingredient. Because not only is there this ingredient in, I don't know, the lasagna you're eating, but it's also an ingredient in, I don't know, the things that they're using to wash down semi-trucks or something, I don't know. But anyway, what I'm getting at with salt is it's actually, who knows the two things that make up salt? What are the two elements? Yes? Sodium chloride, right? And again, we need salt. It's tasty too, on top of everything else. But sodium chloride, right? Sodium is an explosive metal. It's dangerous. If you get it wet, it explodes. It's a very dangerous thing. Chloride is used to make gas. Used in a lot in World War I to kill people. It's a poison. So you have one explosive metal combined with one poisonous gas, and you get something unique. The point is, the individual ingredients don't mean, you know what, SHIT. It doesn't mean anything, right? So don't let people scare you like that. Anyway, let's move on. The rest of that's a little less important. Can anybody tell what metal that is? Yeah, probably copper. And again, I didn't choose these pictures. This came from your old textbook. That's relevant around here, right? A lot of people try to steal copper. Doesn't always work out for them. Anyway, yeah, that's just an example of one of the metals. This one's a little bit harder and a little bit less relevant to you guys because you're from West Virginia, or in West Virginia. How far south did we get? Somebody's from South Carolina, right? Oh yeah, that's very south. Let me rephrase that. How close? Who here is from the closest area to the equator? Where are you from? Oh yeah. That is close. I used to live in Key Largo and Miami. And Tavernier. We should talk. You're not a Miami fan, right? Probably watched that game. Anyway, so what I'm getting at here is because of all the carbon dioxide that we're putting out to the air, even here in West Virginia, right? It mixes in the atmosphere, then the oceans absorb it, and what happens is that produces an acid. And what's happening there is it's killing coral. For you guys, that might not matter. But if you're from Key Largo and that place is based on tourist dollars, a lot of people like to go scuba diving. If you kill that and you kill the tourist dollars, then that's bad for the economy. Anyway, let's move on to it. Here we go. Building blocks of molecules. Oh, excuse me. It's almost impossible to read. I need to fix that for you. This chapter is broken down into 3 main sections that are basically impossible to read. The first one is the building blocks of molecules. Then we'll talk about water. Then we'll talk about biological molecules. And again, sorry this is so hard for you to read, but the learning objectives are, for this section, you should be able to describe matter and elements. You should be able to describe, the interrelationship between protons, neutrons, and electrons, and the way in which the electrons can be donated or shared between atoms. So let's talk about this. This should be a review. You guys have all had a science class before, right? This is not your first science class, maybe in college, but there's no way you could have gone through K through 12 without learning what I'm about to teach you. So let's jump into this review. All right. So each element consists of one kind of atom, right? So gold has a particular kind of atom that's different than lead. It has a different kind of atom, which is different than oxygen, right? Different kind of atom. But what is an atom? You need to know this for the exam. It's the smallest component of an element that retains all of the chemical properties of that element. You could almost say you can't break it down anymore. Actually, you could say that. That's the smallest part of an element, right? If you break that down anymore, which you could break it down, but once you break it down, it's no longer that element. And you'll see why as we move forward. Are there any questions about what an atom is? All right. Who knows what these 3 things are? What 3 things make up an atom? Anybody know?
Proton, electron, neutron.
Yeah, protons, electrons, and neutrons. Very good. You guys probably already know that. You need to know that for the exam. Those are the 3 things that make up atoms. There's actually smaller things than that. You can look it up for independent work. As far as biology is concerned, it's pretty useless. So, and this is a 100 level class, so we're not teaching that. But again, you can look it up for independent work if you want. What makes up protons, electrons, and neutrons? Well, you can look it up. But again, I'm not going to talk about it. I don't want to confuse you. But the subatomic particles that you need to know, again, protons, electrons, and neutrons, you need to know that. Not in that order. There is no order. That just happens to be the order in which I wrote it. But you also need to know their charge and their mass. Charge is easy, in my opinion. Protons, because they start with P, that always helps me remember, are positive. Positive protons, right? Neutrons, as the name indicates, are neutral. By process of elimination, then, electrons are negative, right? So it's easy to remember. Also, getting electrocuted is a negative experience, right? You can look at it that way. Sometimes the harder part is for people to remember that protons' mass is 1, the neutron's mass is 1, and as far as we're concerned in this course, electrons don't have mass because they're so small. Any questions about those 3 parts? You'll get really familiar with them in the next week's lab because we're going to be talking a lot about them. Anyway, here's something else you're going to need to know for the exam and for next week's lab. When you're looking at any particular atom, if the number of protons is the same as the number of electrons, it is neutral, which makes sense, right? Protons have a +1 charge, electrons have a -1 charge, so they would balance each other out. The net electrical charge, if those things are equal, is 0. The atom is neutral. Any questions about that? Now, if I had left it at this, you might incorrectly assume neutral atoms don't get involved in chemical reactions. Because when I think neutral, I think of like, oh yeah, it doesn't react and stuff. So don't let that fool you. That's not the case. We'll talk about that later. But just know that the protons equal the electrons. It's neutral as in it does not have a charge. It doesn't have a positive charge. It doesn't have a negative charge. Its charge is neutral. Make sense? All right. And that's an example. Not that you need to know those examples from the bottom, but there we have a hydrogen on the bottom left. So 1 proton, 1 electron, neutral. Then we have gold next to it. 79 protons, 79 electrons. It's neutral. Because those things balance out. All right. Here's something else you need to know for the exam. The nucleus of an atom, not a cell. The nucleus of an atom is like the middle part, right? That's the central core. And that's where you'll find the protons and the neutrons. The protons and neutrons are in the nucleus. By process of elimination, then electrons must be outside of the nucleus, right? So protons in the nucleus, protons and neutrons in the nucleus, electrons on the outside of the nucleus. I like this picture, not that you need to know this. That's a uranium nucleus with a lot of protons and a lot of neutrons. And think about this, protons are positively charged, right? Sort of like two magnets of the same size or same polarity. So what do you think happens when you try to put two protons together? They repel each other, right? So think about that. Not that this shows the number, but there's 92 protons there, squished together, and they don't want to be together. Right? They're all repelling each other, yet they're squished together. So think about how much energy is there holding that together. Then, if you could somehow break it apart, break some of that off, that's a lot of energy being released, right? Hence nuclear energy, right? That's how we can make electricity and blow up cities, right? Hey, the nuclear energy is actually different than chemistry. Because look, when you break it down a nucleus, not doing chemistry, we'll talk about that later, but nuclear energy as far as this course is concerned is not very important. Anyway, back to what you need to know. Inside the nucleus, you find the protons and the neutrons. Outside, you find electrons. I like this picture. It's a little bit hard for you to see it, but that's not a dirty spot on the projector or the screen. It's like a cloud, basically showing where the electrons most likely are. Later in lab, I'm going to show you a picture. It's going to look like this. Let me draw it here so people online can see it. You will be drawing a model that looks like this. There'll be one ring, and it'll have some electrons on there. Then you draw the next ring, and it'll have some electrons on there. It's not very realistic to what an atom actually looks like, but it's very helpful academically. So we'll cover that when we get there. Anyway, again, for the exam, protons and neutrons are in the nucleus, electrons everywhere else, well, outside of the nucleus, kind of orbiting. For us, we can say orbiting, that's fine. And again, protons are positive, electrons are neutral. Any questions about that?
Do the elements share electrons? Is that what makes compounds?
The atoms will share electrons, so we'll talk about that actually here in a few slides, because that's basically what drives chemical reactions, is that need to share or get rid of or take electrons. It's all about the electrons. Also, I should say this, just in case I misunderstood your question. All electrons, as far as we're concerned, are the same, right? So the electrons in a carbon atom are the same as the electrons in a uranium atom. Now, granted, there's different numbers of them, but they're the same kind of thing, if that makes sense. Did I answer your question?
Yeah.
Okay. All right. Atoms of an element have the same unique number of protons. That's very important. You need to know that. So it's kind of funny because it kind of goes off the question you asked, except now we're talking about protons instead of electrons. All atoms of any element have the same number of protons. Another way of saying that is the number of protons defines the element. So helium has 2 protons. If you take one away from it, you've changed it. It's no longer helium, it's now hydrogen. Right? You can't change the number of protons, keep the same element. That defines it, so to speak. Another very important thing to mention is that thing that we just been talking about, the number of protons, is called the atomic number. So when I say the atomic number of oxygen is 8, what I mean is it has 8 protons. And there's other stuff we can figure out from that small amount of information. We'll talk about that later. But yes, you definitely need to know what the atomic number is. That is the number of protons, and it defines the element. Helium is an example, so I'm going to put an X next to this, meaning I'm not necessarily going to test you on that example. You will get some questions where I say, hey, this thing has this many protons, and its atomic mass is this, how many neutrons will it have, but we'll talk about that later. But I'm not specifically going to ask you anything about helium. But it is an example, so let's talk about the example. Helium, like I said earlier, has 2 protons. If you take one away, it's no longer helium. If you give it another one, it's no longer helium, right? And it's 2 protons by definition. Therefore, again, its atomic number is 2, because those things are the same. The atomic number is how many protons it has. And again, no other element has 2 protons. Because by definition, that's what makes helium helium. That brings us to the next concept, the mass number. We need to know this for the exam. This is the only math you have to do on the exam. The mass number is the sum of the protons and the neutrons. Right? So if I said something has 50, I'm making a number up. this is not, it won't be like this, but if I said something has 50 protons, and it, I don't know, its mass number, it's really hard to draw like that. Its mass number is, I don't know, 100. And then I might ask you, all right, this thing has 50 protons, its mass number is 100, how many neutrons does that, right? So basic math. So then you say, okay, 50 plus what equals 100, right? 50 plus 50. That's the kind of math you have to do on the exam. You get 1 or 2 questions like that, but for some reason you're really bad at even simple math, don't let it stress you, it's just 1 question or 2. Then again, it'll be very simple. So simple that you won't need a calculator. Anyway, any questions about what the mass number is? Again, it's the sum of protons and neutrons. Here's where it gets a little bit trickier. And your textbook didn't explain it, it just mentioned what this next term is and then didn't explain it. So I'm going to explain it, just like the last textbook did. Next term you need to understand is atomic mass. It's similar to the mass number, but the mass number is like you're looking at one particular atom and saying, okay, that one particular atom has that many protons plus that many neutrons. That is the mass number of that one particular atom. The atomic mass, however, is looking at all of them, of that element, and doing an average. And we'll use hydrogen as an example. Its mass number is 1.00784. Now remember, the only thing that has mass in an atom is a proton and a neutron, each of which weighs 1. There are no halves or quarters, right? So nowhere in the universe is there a hydrogen atom that has that mass. There's nothing that weighs 1.00784, right? Nothing exists like that. It's an average. Almost every hydrogen in the universe is this one right here. 1 proton, no neutrons. So a mass of 1, right? Some hydrogens in the universe have a proton and a neutron, so have a mass number of 2. Some, even very rarely, even more rare, have 1 proton and 2 neutrons, so a mass of 3. So they figured out all of the hydrogens in the universe, of all of them, if you were to average them out, that's the number you would get. Does that make sense? So again, there is no single hydrogen atom in the universe that has that mass as its whole numbers. It's just an average. Just like if we measured everybody's height in here, and for some weird reason everybody was either 6 foot or 5 foot, right? When we measured everybody and then did an average, it would probably be like 5.5 feet or like 5 point something, right? It wouldn't be a whole number, though each one of us was a whole number. Same here. Anyway, definitely don't need to know anything about hydrogen. These are just examples. You definitely need to understand this relationship between atomic mass versus the mass number. Any questions about that? All right, this brings us to the next thing that you're probably very familiar with. We have one on the back of the room. It's called the periodic table of elements. I'm almost definitely not going to ask you any questions about the periodic table of elements. You will use it in lecture and lab next week, but it's almost definitely not going to ask you any questions about this on the exam. Maybe on the quiz. Actually, I don't even remember. I need to look at that quiz again. So it's quick. Let's talk about very quickly. It includes the atomic number and the atomic mass of each element, at the very least. If you look back there, it also includes other stuff. Kind of hard to read, especially for me. I'm not wearing my glasses. But it's got a lot of information. Each little square has a lot of information about each element. It provides key information about the properties of the elements. And we won't even get into it, but if you had chemistry, you know, like even where it is on the table tells you something, right? Everything on the left-hand side, the very left, they all have stuff in common. They all react similarly when it comes to chemical reactions. Anyway, shows how the electrons are organized. That'll be very important next week when we do that, when we use the table to answer some questions in lab, not the exam. It provides important details about how atoms will react to each other. So there we go. Here's what it looks like. Again, we've got one in the back. We've got one here. We've got one in your textbook. Next week's lab has one at the very bottom of the document. So there it is, the periodic table of elements. That's it. I'm not going to ask you any questions. I'm not going to ask you anything like, what is the atomic? Unless I give you this, I might, and this is very rare, I probably won't do this either. The most I would do is give you this thing and say, what is the, like for example, what is the atomic number for carbon? And you would look and I go, oh yeah, carbon, atomic number 6. Nothing to figure out, but if anything, I might give you a periodic table and ask you to use it to answer a very basic question. Any questions about that? So whatever you do, don't feel like you need, and I wish somebody told me this when I first studied chemistry. You don't need to make little flashcards for each little element. Like, all right, it's a number, whatever. They can be found here. I'm not going to ask you these questions. Isotopes. This is a term you need to know. An isotope is a different form of the same element. And I showed you isotopes earlier. I just didn't tell you that's what they were called. That hydrogen, remember one of them had one proton, the other one had a proton and a neutron, the other one had a proton and two neutrons. Those were isotopes. Those were the same element. Each one of those things was a hydrogen. Had to be, by definition, because it had one proton, right? We know that the number of protons defines the element. So yeah, it's the different forms of the same element. Specifically, this is a better way of putting it. If you change the number of neutrons, then you get an isotope. Right? So there we go. So far we know this. If you change the number of protons, you get a new element. If you change the number of neutrons, you get an isotope. You need to know that. Same number of protons and electrons, a different number of neutrons. And they basically behave identically in chemical reactions, which I'm not going to ask you that. That is important for people who use isotopes in research. You guys won't be using isotopes in research, so that's not important for you. But yeah, they do, like, so this example between carbon-12, carbon-13, and carbon-14, those are all different versions of carbon, but in chemical reactions, they all act the same. And that's actually really important for people who use carbon-14 dating, for example. Like, we can date and figure out how old some things are by looking at the ratio of something, how much carbon-12 does it have in it, how much carbon-13, how much carbon-14. Those are just examples. Definitely don't need to memorize anything on this table. It's not from your textbook, just an example. So again, what you need to know for the exam is that isotopes have different numbers of neutrons. Any questions about that? All right. Let's see. Again, going off the same example, different isotopes of carbon. Carbon-12 is named after its mass, right? It's 12, right? So 6 plus 6 is 12. 6 protons, 6 neutrons. 6 protons, 7 neutrons gives you carbon-13. 6 protons, 8 neutrons gives you carbon-14. Hence, when you look at the periodic table, carbon's atomic, right? It's the mass is 12.011. Again, not because any one carbon has that mass, it doesn't. But if you were to take all the carbons in the universe and average them, then that's what they would come up with, right? And I can tell you something. I didn't even bring this up. Let me bring this up quickly too. Not that I'm going to test you on this. But if you were to just have one carbon-12 and one carbon-13 and one carbon-14 and average them, obviously the average would be 13, right? Because the average of 12, 13, and 14 is 13. Does that make sense? That's the average. However, what that number indicates is that there's a lot of carbon-12 as opposed to 13 or 14, right? Because the number, that average, is a lot closer to 12 than it is 13 or 14. Does that make sense? Right. Not that you need to know that, but now you do. Now you can decipher that a little bit better. And here's another good example, and then we'll probably be done. How many, say toes, excuse me. How many toes does the average human have? I would think it depends on how you think about the question. You would think, right? But I would say you could reword the question to definitely make you correct if I said, how many toes does the typical human have, right? If you think about it, some people have extra toes, some people are missing toes. So if you were to count all the toes on every single human, and then average it all up, I almost guarantee you it wouldn't be 10. It might be like 10.7 or, I don't know, 9.88, whatever, but it probably won't be exactly 10. That's a big picture. Yeah, so imagine, other people some people do have extra digits or missing digits, right? So again, probably the number is not 10. It would be some partial number. Anyway, same concept here, right? With isotopes. Let's move forward. Yeah. So the last word for attendance is radioactive. And when we get back on Wednesday, we'll discuss radioactive type isotopes very quickly because it's not in the textbook and I won't be testing on it. But that's it for today. So if you need help on the pre-lab, meet me online at 9 a.m. Yeah, that's it. See you on Wednesday. If you came in late, make sure you text me and say, hey, I came in late. If you got those keywords, that'll help you a little bit. We get some of those back. Okay. Yes and no. The one that I can hinge it with, this is the final lab that's testing you on all the labs. Like that. So it'll just be the last lab. Last week. As a matter of fact, the last lab isn't even a new lab. That week after that, like you say, all right, I have to go to the lab. What'll happen is, the last week of lab, you choose a lab that you've already done and turn it in. So if you want, you can choose one that you got full credit on. Oh, perfect. It'll be good. Because the last lab we come together to do will be, I think, before the next semester. And even then, I think it's even a virtual lab. We'll come here.
Yeah.
Students will have the option to do it by themselves. So I'll be, yeah. So. No. Oh, no. Oh, okay. They should let me know. Yeah, sorry. But like I said, even though you just told me, if you don't mind sending me an email, so I have a paper trail. That way if I screw it up, I can look back at my old emails. Oh, yeah, he was here. He definitely sent me an email.